Okay, we're back. This is going to be part 4 of chapter 23 for Bio 221. I'm Jamie Batts, and we just finished our video talking about the different gas laws that apply to the respiratory system. And now I want to, again, just backtrack a minute and talk about some of the volumes and capacities that are listed on 832 and 833. They're very straightforward, what they are, and that graph there on 833 looks like that. This graph here, very helpful in understanding what they are and the units that they are, like how big they are, you know, the kind of average volume that they are. Very, again, very important to understand how that works. So let's talk, just making sure my whiteboard was cleared off. Let's talk about gas exchange and partial pressures. And I think this video is going to be one of the longer ones, but that's alright. So, again, we're going to make a little chart, and we're going to compare the partial pressure of carbon dioxide, oxygen, and nitrogen, N2, in both the alveoli gas, and the pulmonary vein. Right, so this is kind of going back to the heart, right? And then the interstitial fluid. So this is what we're breathing in. What we're breathing in, what we're putting back into the heart to be pumped out to the body, and then kind of what's waiting out in the body. Right, what's waiting to get back into the systemic circuit. So the partial pressure of carbon dioxide that we are breathing in is about 0.3, so about 30% of our air. The partial pressure within the pulmonary vein is 40. And then the partial pressure of the interstitial fluid is 45. So in other words, where is carbon dioxide going? Well, that's easy, right? It's going from high to low. Boop, boop, right out into the alveoli, out into the world. Remember that? Things are going to go from areas of high concentration to low concentration. When we're talking about gases, we don't call it a concentration. We call it a partial pressure. It's just a different term. So that carbon dioxide that's accumulated in the interstitial fluid, this is out in the peripheral cells in the circulation, that's going to go into the blood plasma, float around, come back into the heart, be pumped out to the alveoli, out to our body. Okay. Partial pressure of oxygen. Sorry, I had lost my train of thought there. In the alveoli is 159. Well, in the pulmonary vein, it's 100, but it gets diluted by, remember the pulmonary circulation, there's those pulmonary bronchial arteries that come back up. So it actually goes back to 95 once it's diluted. So it's floating around the body as a 95. And then the periphery, it's 40. So where's the oxygen going? Right? And then nitrogen, just for the fun of it, is 597 in the alveoli, and it's 573 in the pulmonary veins. Very little, 573. Very little of it is exchanged. Again, it doesn't dissolve very well in liquid, so it's not the ideal. On average, only about 50% is saturated at a time. So in other words, think about all of your red blood cells and all of their hemoglobins and all of their hemes, right, ready to hold. You know, each hemoglobin has 4 hemes, and you know there's like billions of them on one red blood cell, and then you have billions of red blood cells. Well, at any given time, only about 50% of them are saturated with oxygen or carbon dioxide. So it's not like every single red blood cell is holding its maximum capacity at every given time. That's when athletic training comes into play. You train your body, you get used to being more efficient, having a more efficient heart rate being more efficient at exchanging the gases, and then your saturation will increase just because your body knows it's going to need it, right? Because you're pushing your body. So just kind of some thoughts there for you. Let's talk about what happens to these gases. Use my very technical eraser here, my hand. Oh. Let's talk about what happens to these gases when they're in your blood. Let's first start talking about carbon dioxide. In the blood, carbon dioxide really has three fates. It can, in the blood, carbon dioxide in the blood has three fates. It can go into the RBC. In other words, it attaches to the red blood cell kind of like oxygen, right? There's two things that could happen in that red blood cell. It could attach to hemoglobin, and that's what it's called, carbaminohemoglobin. A really long word, I'm not going to write it out. Carbaminohemoglobin is what it's called. It's just when carbon dioxide binds to hemoglobin. Or it could interact with, again, this is in the red blood cell. The red blood cell itself has an enzyme called carbonic anhydrase. So it could interact with carbonic anhydrase. I'll show you that reaction in a minute. Or it could dissolve in the blood plasma. The majority of it does this. That's number one. This is number two. This is number three. The majority of it is interacting with the carbonic anhydrase. Some of it is attaching to hemoglobin, and very little of it is dissolving in the plasma. So then we ask the question, well, why does so much of it interact with carbonic anhydrase? That must be pretty important. It is. So let's talk about, do you want to talk about it? Yeah, let's talk about it. Again, I'll erase this on up. So, in the red blood cell, you have carbon dioxide, and there's water also in the red blood cell. There's water everywhere. And when these two interact, and if there's carbonic anhydrase present, which there happens to be in the red blood cell, a very cool reaction takes place. Carbonic. I'm going to write this smaller, sorry. CO2 plus H2O. Interacting with carbonic anhydrase. You see all that? Not really. Sorry. CO2, H2O, carbonic anhydrase. What this creates is a molecule called H2C, CO3. That molecule right there is carbonic acid. And carbonic acid is a weak acid. And if you remember chemistry, weak acids dissolve and dissociate very, very quickly. And that's exactly what this does. It's going to dissociate into a hydrogen ion and another molecule. If we lose a hydrogen here, it's going to be HCO3 minus. And this guy here is, bicarbonate. And he acts like a weak base. So you have a weak acid and a weak base. And this equation happens back and forth, back and forth, back and forth. So it can happen this way, and it can happen that way, and it can happen this way, and it can happen that way. And if you think about kind of function of blood, one of the functions is homeostasis, right? Maintaining balance. There's three main functions of blood: transportation, homeostasis, and protection. Well, this is one of the major functions of blood in terms of homeostasis. We're talking about this reaction of carbon dioxide and water with carbonic anhydrase in a red blood cell. And what is it doing here? It's acting as a, anyone recognize it? It's a buffer, right? And what do buffers do? They maintain a pH. So if there's too much hydrogen ions accumulating in the blood, that means the pH is too low, it's too acidic. Well, guess what? More carbonic acid will be formed, right, to soak up those extra hydrogen ions. And then if there's not enough hydrogen ions, then our carbonic acid will dissociate more to create more bicarbonate to again neutralize the alkaline blood. we have a whole chapter dedicated to homeostasis and specifically acid-base buffers. But this is an important concept to kind of get you thinking about that for the future. That's one fate of carbon dioxide there. Let's see. Let's think about some other things that carbon dioxide does in our body, or influences of carbon dioxide. So your body has chemoreceptors in the medulla oblongata, carotid bodies, aortic bodies, sensing kind of dipsticking in the blood, testing it for carbon dioxide concentration. Carbon dioxide concentration, because of this scenario here, the carbon dioxide concentration in your blood is also linked to your pH. So, in other words, if you have lots of carbon dioxide in your blood, more than likely your blood is slightly acidic. Because of this equation, carbon dioxide acts like an acid in your blood. So if you have too much of it, that's not good. You have to keep it in balance, right? And so because of that, your blood's going to carefully be monitored for carbon dioxide concentration, not just to get rid of it because it's a waste product, right? We'll soon learn that it's actually not a waste product. But it's important to know if you've had too much of it. And that's where the regulation of the respiratory system comes into play. So how is it regulated? Well, first of all, there is a, I'm trying to find the word in the book because I just know the abbreviation. There is a molecule, there it is, called BPG. It's 2,3-biphosphoglycerate. Just BPG is all you need to know. It's on page 840. And BPG is a chemical molecule that is released to help increase the release of oxygen from hemoglobin. So in other words, it's helping to allow your body to put oxygen into the tissues. And so if you have an increase in BPG, you're also going to have an increase in pH, and vice versa. If your pH is increased, your BPG is going to increase. These two are strongly linked to each other. And what that does is it increases the release of oxygen from hemoglobin. It increases the release. And there's all of these oxygen hemoglobin dissociation curves that you'll see in the book. And that's important to understand how those curves function and what they represent. So in other words, how a increased pH or a decreased pH is going to affect how readily your body lets go of oxygen or holds on to oxygen. It's all interconnected and interrelated. So again, very important to understand. Let's talk about some scenarios. I like to think big picture and kind of apply it a little bit. So let's talk about a scenario where we're increasing our activity level. Increasing activity. Maybe we're going out for a run. Today was a nice day. Let's go out for a run. So when we do that, we're increasing our activity level. Our partial pressure of oxygen is decreasing, again, because we're using it more, and because our cells are working harder, they're going to start increasing their production of carbon dioxide, so our partial pressure of carbon dioxide builds up. And so what this does is it forms a gradient. Gradient formed. And basically this gradient is going to lead to an increased oxygen delivery system, oxygen delivery, and an increased carbon dioxide removal. Right? Because we're ultimately exaggerating the partial pressures of these within the tissues, and so that exchange is going to be more efficient. And so what this does is rising O2 levels relax smooth muscles in the arterioles, and that ultimately increases blood flow. Right. Ooh. Rising O2 levels relaxes smooth muscles in the arterioles, which increases the blood flow, and again, that's going to set this back to normal. Right. We're going to get our partial pressures of oxygen and carbon dioxide back to where they should be, comparably speaking, right? We kind of set everything off by increasing our activity. We had to get back to homeostasis a little bit. So that's going to do that. So when you increase the partial pressure of carbon dioxide, ultimately you're going to increase the diameter of a bronchiole. Bronchiole. It's basically your body saying, whoa, we got a lot of stuff here, we got to get rid of it. Let's go ahead and dilate these bronchioles so we can exchange it out and get some good stuff in. So let's talk about how these things are regulated. I said already that there are 3 major kind of chemoreceptors in the body for carbon dioxide / pH. It's all kind of done at the same spot. There's some in the carotid. They're called the carotid bodies. They're little sensors within the carotid arteries. Same thing with the aorta. You have aortic bodies sensing these. And you also have sensors in the medulla oblongata, in the brainstem. So you have respiratory centers in your MO, right, in your medulla oblongata. One is called the DRG. One is called the VRG. Dorsal respiration group. Eek! I think that's what it's called. Yeah, DRG and VRG. Why is this not in your book? It was in my other book. Well, either way, still important to understand how these guys work, even if they're not specifically mentioned in your book. So this dorsal, I think it's respiration group. This dorsal respiration group is basically regulating every cycle of respiration. It's controlling your inspiratory center, because again, when we think about the mechanics of respiration, it's really just inspiration that requires any input. Expiration is completely passive. You just relax everything. Inspiration, you have to contract. Respiration, you relax. And so this is really just controlling your diaphragm and your external intercostals. Right. Diaphragm, external intercostals. The VRG, this is only activated during forced breathing. And I guess the big picture here is this is all controlled through the medulla oblongata, right? Medulla oblongata controls your heart rate, blood pressure, respiration rate. And so you have an inspiratory forced breathing and an expiratory forced breathing, and these are just basically activating those different accessory muscles that are needed in those pathways. So during quiet breathing, again, that tidal volume, quiet breathing, you're doing it right now unless you're out of breath for some reason, your DRG activity increases during inhalation, then you inhale. Then you inhale, and your DRG activity decreases, and then you exhale, right? Because exhalation is passive. So when that DRG, that dorsal respiratory group of your medulla oblongata, is activated, that's when you're going to inhale, and so on and so forth. During forced breathing, it's going to be a little bit more complex. You have to increase the activity in the DRG, and you have to increase the activity in the VRG, and that is going to increase the accessory muscles, and that will allow you to inhale, right? And then your expiratory centers activated, because you can only inhale to a certain point. You can't just inhale for forever. And that's when you exhale. And then the whole cycle can start again if it needs to. So that is all done through the medulla oblongata. Your pons plays a role in regulation as well. So the medulla oblongata and the pons, if you remember your neural anatomy, are very, very close to each other, and lots of pathways cross through those areas. So regulation in the pons kind of crosses over what's happening in the medulla oblongata. And again, things get more complex as you go up in the brain, and the pons is the kind of right above the medulla oblongata. So medulla oblongata has the basics. The pons is going to control what's happening in the medulla oblongata. Make sense? Just like, you know, we can consciously, forcefully inhale or exhale because that's our conscious, then controlling the medulla oblongata. So in our pons, we have two centers. You have one's called the apneustic center, and you have one that's the pneumotaxic center. Well, this apneustic center is in charge of stimulating the DRG. That's what it's there for. The pneumotaxic center is going to inhibit apneustic center. So in other words, inhibit our quiet breathing, our normal breathing, and it's going to promote exhalation. So again, it's another cycle where you have your apneustic center telling your DRG to activating the inhalation muscles, inhaling, etc. Then your pneumotaxic center comes over, allows you to exhale. It's this complicated web of kind of interplay, and really what it is it's cross-checking. It's checks and balances. It's making sure that, you know, not one part is in control of everything, because breathing is so important. It's essential that we have several mechanisms built into our bodies to make sure that nothing is happening incorrectly or the way it shouldn't be. Let's talk about a few more kind of concepts here. I think I'm going to stop this video. I didn't realize I went 21 minutes. Sorry. I will start the next video on more chemoreceptors and more physiology stuff.